560 tons of aluminum, fuel, cargo, and human bodies accelerate down a runway at 290 kilometers per hour, and then leave ground, not gradually, not tentatively. The wheels lift, the gear retracts, and something the size of an 8-story building climbs into the sky at 3,000 feet per minute. What force is holding it up? Why doesn't a heavier aircraft simply need bigger wings? What is actually happening in the 4 centimeters of air above the wing skin right now at 35,000 feet, and why at one specific airspeed does the entire system collapse not slowly, not with warning, but in under 1 second? Lift is the upward aerodynamic force produced when air pressure below a moving wing exceeds the air pressure above it. That pressure difference is its only job: cancel gravity. On the Airbus A380, the largest commercial passenger aircraft ever built, that job requires generating roughly 5.5 meganewtons of upward force at takeoff. To put that number in physical terms, that is the equivalent of suspending 50 fully loaded cement trucks in mid-air using nothing but moving air, not cables, not structure, air moving. The wing that does this job looks from the outside almost absurdly thin. The A380's wing is about 36 meters long from root to tip, swept back at roughly 33 degrees, and at its thickest point, near the fuselage, it measures about 1.5 meters from top surface to bottom. That's thinner than a standard doorway is wide, holding up an object heavier than the Eiffel Tower. So the obvious question becomes, how? And the answer that almost everyone learned in school, the answer printed in textbooks, displayed on classroom posters, taught to generations of engineering students, is wrong. Here's the story that got repeated for roughly 80 years. Air hits the wing's leading edge and splits. The top surface of the wing is curved, longer than the flat bottom. Air going over the top has more distance to cover, so it speeds up to arrive at the trailing edge at the same time as the air going underneath. Faster air means lower pressure. That's Bernoulli's principle, and Bernoulli's principle is real. Lower pressure on top, higher pressure below, wing gets pushed upward. Clean, logical, the equal transit time model, the idea that the top and bottom parcels of air must reconverge at the trailing edge, has been disproven by direct observation. When researchers traced airflow with dye and high-speed cameras, the air traveling over the top surface arrived at the trailing edge significantly earlier than the air traveling underneath. The two parcels do not meet. They never did. The equal transit assumption was a convenient story that produced the right answer: a pressure difference, through entirely the wrong reasoning. NASA published corrections to this model in the 1990s. The textbooks that carried the myth were still in classrooms for years afterward. But here's where it gets complicated, because Bernoulli isn't wrong. The pressure difference is real. The mechanism that creates it is just far more interesting than the story suggests. The actual explanation has two separate engines running at the same time. The first is the shape of the wing, what engineers call camber. The top surface of a wing is curved, and that curve forces air to change direction as it flows over the wing. Changing direction requires a centripetal force directed toward the center of the curve, which means the air pressure above the curved surface must be lower than ambient. The suction exists because of the geometry, not because the air is trying to keep pace with anything. The second engine is angle of attack. The wing is tilted, leading edge up, trailing edge down, and this tilt deflects a massive column of air downward. Every kilogram of air that gets pushed down means the wing and everything attached to it gets pushed up. Newton's third law, applied at industrial scale. An A380 at cruise is deflecting hundreds of tons of air downward every second. The wing is not slipping through the sky, it is actively redirecting it. This is the part everyone misses. The suction above the wing is not a side effect, it is the primary mechanism. At cruise, the low-pressure zone on the top surface accounts for roughly 2/3 of total lift. The high pressure pushing up from below accounts for only 1/3, which means the wing is being pulled upward more than it is being pushed. And it means that anything that disrupts the airflow on the top surface, ice, damage, contamination, the wrong angle, has a disproportionate effect on whether the aircraft stays airborne. Every time a wing generates lift, it also pays a tax. At the wingtip, high-pressure air from below the wing spills up and around toward the low-pressure zone on top, forming a rotating column of air that trails behind the wingtip like an invisible tornado. This is called a wingtip vortex, and it is not small. The A380's wingtip vortices extend for up to 900 meters behind the aircraft. That's 9 football fields of rotating air, powerful enough to flip a light aircraft even when encountered from 3 kilometers behind, 3 minutes after the A380 has already passed. This is why air traffic control enforces separation rules that exist for no other reason than vortex danger. The spinning wake of a large aircraft is a physical hazard with a radius measured in kilometers and a lifespan measured in minutes. That spinning wake also costs energy. Every vortex represents lift that leaked sideways instead of going up. Engineers call this induced drag, and it scales with how hard the wing is working. The harder you push for lift, the more you bleed to vortex losses. This is the entire reason winglets exist. Those upturned tips you see on nearly every modern commercial aircraft are not aerodynamic decoration. They do not increase lift. Their only function is to interfere with the formation of the wingtip vortex. To partially block the spillage of high-pressure air from below to low pressure above, a well-designed winglet reduces induced drag by around 5%. On a 15-hour intercontinental flight, 5% drag reduction saves roughly 3,000 kilograms of fuel per trip. That is the weight of a small car, saved on every single long-haul flight by a curved metal fin about 2.5 meters tall. So that is why a 500-ton aircraft has wings shaped like a bent parentheses at the tip, not for aesthetics. For vortex suppression at scale. The closest thing most people would compare a wing to is a helicopter rotor. Both generate lift. Both rely on a pressure difference between the top and bottom surface of a moving blade. But a helicopter rotor is, in every functional sense, a rotating wing. It generates its own relative airspeed by spinning, which means it can hover with zero forward velocity. A fixed wing generates zero lift at zero airspeed. An A380 sitting on the runway is not generating any meaningful upward force, regardless of how aggressively the engines are running. The wing only works once the aircraft is moving. A helicopter generating 10 tons of lift uses a rotor about 14 meters in diameter spinning at roughly 250 revolutions per minute. An aircraft generating the same 10 tons of lift uses a fixed wing at 280 kilometers per hour, same lift. Completely different method of creating relative airflow. The surprising similarity is that both systems pay exactly the same vortex tax. Helicopter rotor blades produce wingtip vortices too. The characteristic rhythmic chopping sound of a helicopter, the one everyone recognizes, is largely the sound of a rotor blade passing through the vortex trail left by the blade that came before it. Same physics, same penalty, just louder. The contrast with a glider is equally useful. A glider produces lift in exactly the same way as an A380. Same Bernoulli, same Newton, same pressure differentials, same wingtip vortices. The difference is energy source. An airliner uses thrust to maintain the airspeed that generates lift without descending. A glider converts gravitational potential energy, altitude, into the forward speed that keeps lift alive. A glider and an A380 generate lift in exactly the same way. One just refuses to descend. The best modern gliders achieve lift-to-drag ratios above 60. The best modern airliners achieve roughly 21. A glider aerodynamically is a more efficient flying machine. It just cannot carry 555 passengers across the Pacific. Here's where it gets crazy. December 17, 1903, Kill Devil Hills, North Carolina. Orville Wright lies face down on the lower wing of a fabric and spruce biplane weighing 274 kilograms. The engine, a 4-cylinder block that Orville and his brother built themselves in their bicycle shop, produces 12 horsepower. That is less power than a modern riding lawnmower. The wind is cold and steady at about 27 kilometers per hour. At 10:35 in the morning, the aircraft travels 36 meters and stays airborne for 12 seconds. The Wright brothers have done something no powered heavier-than-air aircraft had done before. What they do not yet understand, what no one yet understands, is exactly why it worked. The Wright Flyer's wing had a lift-to-drag ratio of approximately 6:1. For every 6 newtons of lift it generated, it lost 1 newton to drag. Modern commercial airliners operate at lift-to-drag ratios between 17:1 and 22:1, meaning they produce roughly 3 times the lift for the same drag penalty. That gap between 6 and 20 is not the result of better engines or stronger materials. It is the result of mathematics that did not yet exist in 1903. The Wright brothers had no formula for induced drag. They discovered their wing geometry empirically by testing over 200 wing shapes in a homemade wind tunnel the size of a shoebox, logging results by hand, crashing repeatedly, and revising. The math that would have let them predict optimal wing shape before building it was still 15 years from being written. In 1918, while the First World War was still active, while aircraft were being shot down over France in numbers measured by the hundreds, a German engineer named Ludwig Prandtl published his lifting line theory. This was the first mathematical framework that could simultaneously predict the lift a wing would generate and the induced drag it would produce before the wing was ever built. It described in precise equations why a tapered and slightly swept wing was aerodynamically superior to a rectangular one, why wings should narrow toward the tip, why they should be longer relative to their width, why the elliptical lift distribution achieved by a properly shaped wing minimizes induced drag for a given amount of lift. The Allied powers Britain, France, the United States were at war with Germany when this theory was published. They used it anyway. Every commercial wing built since 1920 uses tapered, swept geometry. Prandtl's equations proved it was optimal. That theory, written by a German mathematician during a world war, is the reason every commercial aircraft in the sky today has the wing shape it has. When a commercial flight's severe turbulence over the Pacific and the overhead bins rattle and the passengers grip their armrests, the wings are flexing upward at the tips by up to 6 meters. That flex is not a structural failure warning, it is designed in. Rigid wings would snap under the same loads. The flex absorbs energy that would otherwise fracture metal. Every time a passenger glances out the window during takeoff and watches panels extending from the trailing edge of the wing, those are Fowler flaps, and they are increasing the wing's effective surface area by up to 25%, generating enough extra lift to allow the aircraft to fly safely at a lower speed, which is the only reason 500-ton aircraft can operate from runways that are not the length of a motorway. When an airliner lands in a crosswind and the nose points sideways relative to the direction of travel, the pilot is managing the angle of attack asymmetrically across both wings to counteract lateral drift. The same physics that makes the aircraft turn is being used to hold it straight while touching down crooked. When a plane levels off and the engine noise drops, that reduction is not only the pilot's reducing throttle, it is also a reduction in angle of attack. At cruise altitude, the air is roughly 30% less dense than at sea level, about as thin as standing on top of a mountain 30,500 meters high. To generate the same lift from less dense air, the wing needs either more speed or a greater angle. Cruise speed handles part of it. The rest is angle. Here's the surprise. When de-icing trucks spray aircraft before departure on a cold morning, they are not primarily protecting the fuselage or the engines. They are protecting the top surface of the wing, a layer of frost 0.5 millimeters thick, thinner than a credit card, disrupts the smooth, laminar airflow over the top surface that generates the suction zone. That disruption can reduce lift by up to 30% at the speeds required for takeoff. A half millimeter of ice can make a fully fueled, fully loaded commercial aircraft unable to get safely airborne. When military aircraft fly in tight formation, the pilots of trailing aircraft position themselves slightly behind and to the outside of the leader's wingtip, inside the zone of updraft created by the leader's vortex. Free lift donated by the aircraft ahead. Migrating birds fly in V formations for exactly this reason. They discovered the technique roughly 50 million years before aeronautical engineers formalized it in mathematics. When a pilot declares an emergency and dumps fuel before landing, they are reducing the aircraft's weight because minimum safe landing speed, the lowest speed at which the wings generate enough to maintain controlled flight during the approach, scales directly with mass. A lighter aircraft stalls at lower speed. A lower stall speed means more margin before the wings stop working. And when an aircraft descends on final approach with the engines near idle, the wings are still generating lift from airspeed alone. Thrust is only controlling the rate of descent. The aircraft is not falling. It is choosing precisely how fast to come down, which raises the constraint that every aircraft, every flight, every second in the air is negotiating. To generate lift, you need airspeed. To maintain airspeed, you need thrust. To generate thrust, you burn fuel. To carry fuel, you add weight. To carry weight, you need more lift. More lift means more induced drag. More drag means more thrust. More thrust means more fuel. And the wing that provides that lift has a hard ceiling. Push the angle of attack past roughly 15 to 17 degrees and something breaks. The smooth airflow over the top surface, the laminar flow that creates the suction zone that generates 2/3 of total lift, detaches from the wing entirely. It does not thin out. It does not weaken gradually. It separates and the pressure difference collapses and lift drops by 75% in under 1 second. This is a stall, not an engine failure, not a structural failure. The wing simply stops being a wing, and the only recovery is to reduce the angle of attack, to point the nose down, to trade altitude for airspeed, to rebuild the flow and the pressure before the ground arrives. 1 aircraft. 2 rules: generate enough lift, and never let airspeed fall below the speed where the wing stops working, both applying at the same time from the moment the wheels leave the runway to the moment they touch down again. And here's how that tension is finally starting to resolve. Conventional aluminum wings are close to their ceiling. The gains that come from optimizing sweep angle, winglet geometry, and surface finish are now measured in fractions of a percent. The theoretical tools have been refined for over a century, but the physical material, aluminum, has a fixed weight. Every kilogram of wing structure is a kilogram that generates no revenue and produces no lift. So the aerospace industry's current focus has shifted from the shape of the wing to what the wing is made of. The Boeing 787 Dreamliner uses wings built primarily from carbon fiber reinforced polymer, a material made from woven carbon strands embedded in hardened resin. These wings are roughly 20% lighter than equivalent aluminum structures and can flex further at the tip without accumulating metal fatigue. The 787's wings flex approximately 7 meters from tip to tip in severe turbulence by design, not by accident. Airbus has been running a program called Wing of Tomorrow to develop similar all-composite primary wing structures for the next generation of narrow-body aircraft. Fully composite wings with no metal load paths anywhere in the primary structure exist in experimental aircraft. Production readiness for commercial scale is still years away. The trade-off is shrinking, but it hasn't disappeared yet. A 500-ton aircraft stays in the air because it is continuously outrunning gravity, Every second is a controlled negotiation between speed, angle, and pressure. Every commercial flight that has ever landed safely did so because two American bicycle mechanics and one German mathematician each solved half of the same equation, separated by 15 years and a world war. The wheels touch down, the spoilers deploy, the wings release the sky.